in a strange order. So let's go ahead and discuss this because I think a lot of the all right, that was like 20 seconds late on that was weird. So anyway, pH pKa relationships, a lot of this has been discussed already, so I think we can move through this relatively quickly, but I think you should pick up a few more nuggets, so to speak, of some information that you might be able to use in some of our earlier things. Okay, we've got to keep track of all of the relationships. I think that's one of the things that's very difficult. There was a lot of practice in the first couple of sections. Hopefully, you are understanding that. Please reach out if you are not. pKa is equal to the negative log of Ka. That's the relationship that they have. And Ka is our tendency to dissociate. So a large Ka value means that we have a large dissociation. Strong acids and strong bases, we don't even give a Ka value or a Kb value for those because they fully dissociate. They separate completely. And ones that are very weak have a very small one. Of course, water, Kw, which is again the same kind of thing as a Ka or a Kb, it's just the K value is that it is 1 times 10 to the negative 14th at 25 degrees Celsius. What does that all tell us? It tells us water doesn't dissociate well. It also tells if you have an acid with a Ka value of 4.2 times 10 to the negative 5th, it doesn't dissociate very well. But compared to water, it is more. Since pKa is the negative log, a lower pKa is a stronger acid because remember, there's an inverse type of relationship when we're taking the negative logs. A higher pKa is weaker. Okay, when you look at all of these and how they're related to each other with some graphs, hopefully this will start to make some more sense. Okay, so the relative concentrations of our acid and its conjugate base, we can predict those by comparing the pH of the solution to the pKa of an acid in the solution. So if the pH is less than the pKa, the acid form has a higher concentration in the original solution. And if pH is greater than the pKa, then the conjugate base form has a higher concentration. And remember, when we have a weak acid, we have a strong conjugate base, and vice versa. So looking at these, okay, so this is the degree of titration, just basically kind of an arbitrary value of now it's fully titrated. This is past the equivalence point. So a weak acid and a strong base, we start off higher up. We end up having a higher pH. If our pH is greater than our pKa, that indicates that our conjugate base is stronger, which makes sense. Okay, on this side, we have a weak base with a strong acid. And so our pH is starting off very high. Again, pH is greater pKa. Okay, it's going to have to deal with all of those things too and be the opposite. With this case, it would be pH being less than your pKb. Okay, so don't worry about that. Let's just focus on pKa. So here's an example, multiple choice. Student pours 20 milliliter sample solution containing formic acid, and it has a pKa value of 3.74, and sodium formate into a test tube. The student adds a few drops of methyl orange to the test tube and observes a red color, which indicates that the pH of the solution is less than 3.2. That should always be a flag saying that is still pretty acidic. Okay, based on this result, which of the following is true about the relative concentrations of the acid and its conjugate? Okay, the conjugate salt here, which is combining with sodium in its original solution. So do we have more of the acid than the salt? Do we have the same amount? Do we have more or less than the other? We cannot be determined. Okay, so look at your pKa. pKa is relatively low. So if you have a low pKa, your pH is greater. Okay, and then we have the pH. So pH is less than your pKa. If pH is less than pKa, the acid form has a higher concentration in the original solution. And there's our answer. This is the original acid, has a greater than the conjugate base. pH of the original solution is lower than 3.2 as evidenced by our methyl orange change. Since pH is less than pKa, there's a higher concentration of formic acid than the formate ion. Looking ahead. All right, this is a very long free response question. Let's go through some of it. Watch it if you want. We have a solution of 1 molar hydrochloric acid and 1 molar, 0.1 molar of each of sodium hydroxide. Strong acid, strong base. 40 milliliter sample of one of the solutions is added to a beaker and then titrated with the other. It doesn't tell us which one was which. You can tell that we're starting off with our pH being low, so it looks like we were adding the sodium hydroxide as we went. Identify the solution that was initially added to the beaker. Oops, I just answered that. Explain your reasoning. So we start off, the beaker is full of initially added, we have hydrochloric acid, and then it was titrated with sodium hydroxide. Circle the point that corresponds to the equivalence point. Okay, see if you can figure that one out. Stop this at any point. Equivalence point is right here in the middle. How many moles of titrant have been added? You can do a calculation knowing that you have 40 milliliters of solution that has been added. Okay, we'll work through that in just a minute. I don't need to read all the questions. Let's go. Identify your solution that was initially added to the beaker. The solution in the beaker was hydrochloric acid because the initial pH was very low, which is what we talked about. And then we slowly have added sodium hydroxide. I do like that this lady gives you, she does a great job in telling us all of the points that we would be given and how it's actually graded. Circle the point that corresponds to the equivalence point. That looks like an eyeball now. That's a little creepy, but the equivalence point makes sense. Strong acid, strong base, right in the middle, pH 7. All right. How many moles of titrant have been added? Okay, so again, we've got our 4.04 liters or 40 milliliters. We just multiply that times our molarity. And molarity, when we say that it's a 0.1 molar, it's like saying we have 0.1 moles of sodium hydroxide per every liter. We cancel things out, and we had 0.004 moles of sodium hydroxide. The same titration is performed again, this time using an indicator. Use the information at the right to select the best indicator of the titration. So we want to figure out when we're going to see a change. If we use methyl violet, it starts off at 0 to 1.6. I mean, that's not going to show us a whole lot. Methyl red, we would be able to go between 4 and 6. That's going to show us when something happens. And alizarin yellow. Okay. Next one, a solution of the 0.1 molar hydrochloric acid and a 0.1 molar sodium hydroxide. 40 ml sample of one of the solutions is added to a beaker, then titrated with the other. A pH electrode is used to obtain the data. Sketch the titration curve that would result if the solutions in the beaker and the burette were reversed. So now what you're doing is you're starting off with sodium hydroxide in the beaker and you're titrating it with hydrochloric acid. Excuse me, it is going to look the opposite. Okay, there it is. Hiccup. 1 point starting between 12 and 14. Another point for locating the equivalence point is at 7, and then finishing out. That's a 3-point question, and not a very hard one if you understand what's going on with this. She gives a very nice summary here at the end, and so let's take a look at that. The protonation state, we can say that means like where it is, whether it's an acid, a base, how much it wants to hang on to that. We can compare the pH to the pKa. When the pH is lower than pKa, it has more acid form than the base form. When pH is greater than pKa, the base form has a higher concentration. And we can use various indicators. She does not go into a huge amount of depth on the indicators, but I do encourage you to watch those videos. I think she mentions more than what I did here. Thank you for being with me on this journey.